Neurips 2024, part 6. This paper is about math, large language models and math. The title is Learning to Grok, Emergence of In-Context Learning and Skill Composition in Modular Arithmetic Tasks. So fundamentally what these people are doing is trying to understand how math works in transformer-based models and what kind of model design helps solve what kind of math problems. So let's lean back for a second and think about, okay, first and foremost, what is math? Right? Math is different things for different people. And you know that from grade school, high school, university, math has different forms, right? Some math is arithmetic or advanced arithmetic, calculus, differential equations. You put numbers into something and then you get results. Other types of math is more artistic, proofs, for example, proof finding. And then there's math in physics, which tries to describe things. It's more poetic. You try to understand what you see, what you observe in experiments, and try to formulate it in math. For example, quantum mechanics is a good example where Dirac came up with his own notion of how to describe these things. We had to invent imaginary numbers to describe certain phenomena that then led to advanced math in, let's say, wave functions and things like that. So different math, different problems. Now this paper, which comes out of partly Meta, so Facebook, and partly University of Maryland and things like that. So this is a sort of combined work. And what's interesting about this paper is that they look at how can we train a model so it can do math and generalize out of distribution. In other words, is there a way to train a model that can really start doing more math than just what it's trained on, right? So the equivalent would be that if I teach a person how to do arithmetic, can they potentially do more advanced arithmetic? So it's things that they haven't been trained on. And could they potentially, from learning arithmetic, also learn how to do proofs and really do the whole complex part of geometry and all kinds of math? So this is the question. I mean, it's an open question. We don't even know it for humans, right? We don't know if math is a skill composition task or it's just you have the talent and you're good at it and there's an underlying latent sort of eigenvector that defines whether you're good at math or not. We don't know that, and we don't know that for humans and we don't know that for machines. We have a sort of hunch for humans. People are really good at math. They're really good at most things. But then there's, anecdotally, I used to have a girlfriend. She was very good at calculus, but horrible at numerical analysis. So it's not so clear, right? Not every math problem is suited for every person. Back to the model here. So what they're doing here is first they define a specific task, which is some sort of arithmetic mapping. It doesn't matter what the exact task is, but think of this following. There's three types of big picture questions you need to solve as a model designer when you even do math. One is, what's the problem? So a problem would be regression or differential equation or proof finding. So that's the problem. Tasks will be within the problem. So now we're dealing with regression, but we have different types of regression, right? We have a regression, a quadratic regression, linear regression, stuff like that. Linear regression with different formulas. And then we have experimental data. So now we have, we fix the task, we fix the problem, and we feed a lot of data. And all of these things have an impact on how good the model does. I think the conclusion, let me just get to the conclusion here, is that what you really need in the end is you want to have a lot of data and a lot of diverse tasks. Now you can also extrapolate this to diverse problems, and I think this is the next step. This is not what this paper is focusing on one particular problem. I think they call it arithmetic mapping. It's a very specific math problem where you kind of have a grid with numbers, and they represent some sort of input, a variable ax plus by and it's modulo p, which is the dimension of that grid and things like that. But doesn't matter. Links in the show notes. Check out the exact problem. But think of it just again, the problem could be a regression, it could be a quadratic regression, it could be a differential equation. That's the problem. The task is within the problem. We have different versions of the problem, and then we have more data fed into existing types of tasks. And what we show is not very surprising, is that what we want to have is a very diverse task in training and lots of data. If we have that, we have a better chance for generalization. And the reason that happens is, and there's a very important sentence, we observe a clear memorization generalization transition as task diversity increases. So the fundamental problem with any kind of AI model is how much memorization is it doing? And by the way, even if it's doing memorization, what is it memorizing? Remember the tank problem, where we try to identify Russian and American tanks, and what the model actually memorized was the dark clouds of the Russian tanks and the sunny sky of the American tanks, because the training data from American tanks was made in the desert and the Russians were made somewhere in Russia. So it memorized something, and it was even the wrong thing to memorize, but it still got a lot of good test results. So we want to solve that problem, right? We want to make sure that the model doesn't just memorize. Now, at the margin, you could say, if I can feed the data all possible data points and all possible tasks and all possible problems that math has ever encountered, then potentially all it has to do is just memorize. But maybe we can have more sample efficiency, which is maybe we can train with less data, less problems, and less tasks, and still get, because if we can get generalization, we can still get good performance. So this is kind of a trade-off. You know, Sarah Fryer, CFO of OpenAI, that's what she's probably thinking. Like, look, how much money do we spend for training, and can we do more? Can we do better with less money spent? Less, you know, this is sort of the conversation token per dollar, which is what Jensen Huang wants people to do, which is train, and I'll give you the best model to reduce token per dollar. Versus OpenAI wants to have solutions per dollar, which is, okay, I don't necessarily need tokens. What I need is solutions. So I guess what the findings are is that when you design a transformer-based, let's say a large language model, transformer-based AI to do math, you want to think about two fundamental things. One is the attention layers, and the other is depth. The attention layers help you with mapping. So they're going to be very helpful when you want to sort of sort things out. What belongs to what, which, you know, is the word attention. Excuse me, it's not the attention layers, it's attention heads, right? What kind of attention are we paying to what? That's, you know, inherently mapping. And then the multi-layer perceptron, the MLPs, and the depth of the model will help you with sequential things like arithmetic, multiplication, those types of things, or just general logic, compositional logic, right? If I have this, what then? So that you know, by nature is sequential. So we want to have some sort of depth, and the more deeper, the more depth we have, the more deep the deep learning model is, the more sequential logic we can have. And the attention heads are more for the mapping, and the combination helps us solve fundamental mathematical problems. I think I want to mention one more thing, which is not mentioned in the paper explicitly, but the tokenization problem. The tokenization problem has come up in, let's say, GPT, for example. Karpati has spoken about this, which is, why can't GPT-3 do math, arithmetic? Well, it's because the tokenization is such that we don't capture one integer. We sometimes tokenize number with 2 or 3 integers, because that's how words are tokenized. You know, words are not tokenized per letter. And because of that, also the numbers in the training set, when the numbers are fed into training set, numbers, let's say the number 115 is tokenized in maybe 1, 1, and then 5, and then space, or something like that. So that's why the model doesn't really learn how to do math really well. So how do we solve that problem? Well, one is, okay, we can tokenize per integer, but then that is very expensive. So maybe we can find ways to maybe classify numbers, right? Classify what is a number, and then once we know what a number is, we can then deconstruct the number into what it actually means. So 115 in a text, right? If I have let's say a text which says, if I add 115 to 2, I get 117. Like, that's something that GPT-3 doesn't understand. But it could be understood if we contrast the letters and the numbers, and then we realize that the numbers are supposed to be added, and then there's a specific function adding, and then you add. What this paper does really well is also understand in-context learning versus compositional learning. And let me explain what that means. In-context learning is, and again, at the margin, it's probably the same thing, but for simplicity, we separate. In-context learning is that I've trained a model, and now I want to have a specific prompt design to extract more knowledge from the model. That's in-context learning versus compositional task, skill composition, is that I have certain skills that are inherent in the model, and if I combine them, I can then solve bigger tasks. The ultimate example would be that I want to do math, and I can actually write a Python example to solve the math problem. It's a bit cumbersome. Kolmogorov complexity goes up, but it's still doable. And of course, we can maybe do better in the future. But that's kind of the way this paper explains the math problem. I think I'm very curious about math problems in general, because I think that math is one of those things that we will most likely solve to the point where it just becomes an art, and where the real math, which is sort of the what I mentioned in the beginning, the poetic side of things, where we try to explain physical phenomena with better mathematical formulas, for example, that is going to be the actual math that people are doing. And a lot of the heavy duty work, the hardcore multiplications, additions, design, differential equations, finding the right arithmetic context to solve a certain problem, those types of things I think will be solved in maybe 1 or 2 years, particularly with the new reasoning models that are coming out from whether it's OpenAI or others. Versus the real interesting tasks of the future of math will be the poetic side, the description of things. So we have 3 levels of math, if you will. The lower level, which is the actual tooling, the functioning. Okay, which formula solves which problem, and how do I actually solve it? Sometimes it's just, how do I actually solve it? How do I solve this massive, monster of a formula? The second higher level problem is, okay, what is the most efficient way to tackle this problem? And third is, what is the problem in the first place? What kind of math should we use to describe the situation? So to summarize this paper, LLMs for math, it's a mechanical paper. It explains how we can get model design in the transformer world such that certain math problems can be solved. And the conclusion is that it depends on the problem, it depends on the task, and it depends on the training data. And in particular, we want to have a diversity of tasks so we can have generalization, because the key is out of distribution generalization, so we can do things that the model hasn't been trained on. That's the key. And we can achieve that by paying close attention to the attention heads and to the depth, to the multi-layer perceptrons. And I think finally I want to say I think math is going to be automated to the point where we're going to be, very similar to language and programming, where the skill of the human will be to apply all these tools to new problems and to decide which of these tools is most adequate to solve which problem. So the question of which problem are we solving is going to become key in the world of science, and then the actual tools will be done by the AI. Thank you.